this study was done in Germany, and Teresa recruited 6 professional programmers to actually do the study. And then there were 14 true novices. And I say true novices because these students, they were part of a Java course that they just signed up for in the university. They had no knowledge even of block programming. Okay, so they were truly novices. I'm going to keep you can read the paper for more details, but I'm going to keep just the main points here so we get to the results. The way we operationalized linearity was using a bunch of metrics after debating back and forth as to what these should be. And remember, this was a team that was spread out. So I still remember being on the phone with Teresa and Andy discussing these different metrics. But we came up with 5 of them for linearity. So we have vertical next text, which basically is the percentage of forward saccades that stay on the same line or move one line down. Vertical later text is the percentage of forward saccades that stay on the same line or move any number of lines down. Horizontal later is the percentage of forward saccades within a line. Regression rate is the percentage of backward saccades. So if you look back, so let's say you're on this line here and you look back up any number of lines, that is the regression rate. And then the line regression rate is just within the line that you look back. The reason why we looked at regression is because if you go and reread something, that means you're usually having difficulty in understanding it, unless it's, of course, tracing a for loop. In that case, that you might just be looking at it over and over and not necessarily having a problem, but you're tracing it. So the task you're using this for is also important. And then we have a saccade length, which is basically just the Euclidean distance between 2 successive fixation points. We also look at element coverage to see how much coverage do people spend on text and code. So, and I show you a visualization there of a regression. So you can actually see if you go back after looking at the bracket to static and public, then you've made 2 regressions basically. So we just calculate this as a percentage and for each of these dependent variables. So let's get right into the results. So what we found with respect to regression rate in particular, if we just look at natural text and code, we found that in source code, the regression rate was much more, 27% for the early novice, compared to the natural text, which they didn't go back as much. Experts, on the other hand, when we blocked it by experts, we found that the experts tended to have a higher regression rate. And we mainly think this might be because of the way they were tracing the code to get an answer. Because one of the questions in this study was, what is the output? And so you have to trace it. This is the means for each of the dependent variables that you can see. Most of them were pretty significant, except the line regression rate. We couldn't find any differences based on how often they went back on the same line, but everything else was pretty significantly different. With respect to element coverage, we found not everything is looked at. In fact, 31% only of tokens were looked at. In this case, you notice that people generally don't tend to look at the brackets and the public and basic boilerplate code. They do so. So this also relates to the one of the drawbacks of an eye tracker. An eye tracker tells you what you're looking at, but it does not necessarily tell you that you looked at something in your periphery, right? Because if I'm looking straight in front and I see something with high precision, I might see something on the side with less precision in my periphery, but I might still be able to tell what it is based on, its shape, its color, and so on. So this could happen also in code where you don't necessarily look at a bracket, but it's there. We found that with respect to coverage, the programmers looked at much fewer elements. So you can see that in natural language text, it was approximately 80% that they looked at, but in code it was 60. And then novices tended to read much more irrelevant things. That's why you see them reading 52 compared to now experts that read only 41. So then we also wanted to determine if code was similar in reading top down, left to right. So we looked at story order and the execution order. In order to do this, if you can think of the lines 1 to 5 as actual source code lines and the little dots as fixations, you can see the person first read line 4, then they jumped to 1, stayed there for a while, then went to 2, 3, 4, went to 3, 4, and then went back and did another scan down. The things that I highlighted in an oval, they are called a scan pattern. And basically what we tried to do is figure out an automatic way to identify this pattern in the code, in the signal. So this is derived directly from how you compare DNA sequences. It uses the Needleman-Wunsch algorithm actually to, given a gaze and given a model. So let's say if you wanted to determine story order, a model would be 1, 2, 3, 4, 5, because that's how you'd read it, top to down. And then we would try to form a match and calculate a similarity score. The Needleman-Wunsch alignment score, basically it gives you the higher the number, the more similar they are. The paper has details on how this is calculated, but we basically came up with a scheme of, give +3 if there's a match, -3 if there's a mismatch, and then -1 for a gap, and so on. The dynamic approach finds the optimal number of repeats. So it iteratively appends a copy of the model and computes the similarity score until the lengths of the gaze and the model align. Okay, so what we found is early novices mostly follow the story order. Experts follow the execution order. Yeah, and this was a really neat result because we didn't really find this linearity operationalized before. So the contributions of this paper, remember, these were all images. This was not, this was just borrowed directly how code was, or eye tracking studies were done in psychology. This paper was in 2015. So we operationalized linearity by checking and looking to see how people read code in the story order and execution order. And then we validated them on natural language text as well as source code. We looked at differences that exist between novices and experts, true novices and experts. And then we also wrote we adapted the Needleman-Wunsch algorithm for our approach to automatically detect this order in reading patterns. And we do have a replication package for this that's listed in the paper. So the summary is that we now can say for certain that reading code is less linear than reading natural text. And when you read code, you typically skip a lot more compared to natural language. And note that this natural language was English. We did not look at it in any other language. So it could be different in a different language, let's say German or Japanese or some other language. And then experts' reading behavior is better explained by the execution order, meaning the control flow rather than of the program rather than the story order. So what can this have? What implications can this have for our stakeholders? And in particular, I care more about the practitioners and educators. So as a practitioner, maybe we can use these results to evaluate coding standards and describe, certain practices for readability. Or as an educator, you can teach people how to read the program the way an expert was reading it. Maybe even show them an example of how that's done. And eventually, right now we are lacking theories that explain this. I mean, we borrow theories from other fields and try to hypothesize about them, but I think doing more of these studies can actually help us build new theories that explain the differences in behavior between experts and novices. Because one thing I found doing these studies, I've been doing eye tracking studies since 2009. One thing I found is that when I look at two experts and the way they solve a task, they both get the bug fixed, let's say, but they do it in very different ways. However, there is a commonality, and that commonality, though, is not at the raw level. It's at a much more abstract level. of what they're looking at. And how do we come up with that? We need more studies to actually generalize it. We do not have enough data to come up with that at this point. So that was the past. So I'm going to talk about the pain that led to the present. Okay, so since 2016, but I'm going to talk about what was the pain for me, at least as a student. We had these images, as you can see here. We had to literally draw this. I remember drawing these things in, I used Toby Studio at the time because I had the Toby tracker at Kent State. And I literally had to draw this for every single code snippet that I had, the little rectangles. At that time, we didn't have the automatic OCR and whatnot we have recently. So the problem was that we had to do this. So I had this is another example. You had to do this for every single snippet of code that you provided. Okay, and it's error prone, first of all. You have to make sure you're doing it right. You have to make sure the spacing is correct. And then I want to compare that with areas of interest in psychology studies. So you saw, I'm going back one, you saw the advertisement on the right, the baby and the AOI over there, which is the face, the caption, and the shampoo bottle. Look at the areas of interest on the left. Again, nothing like the picture, right? So they are very different, almost like you're reading. So even in psychology, when they use videos like the one on the right, you see that there's a beach, a sea, a sky. They're still broad enough that they are relatively in the same place. So you can use keyframing to actually determine where an object has moved. And the software does that for you. The point is that the areas of interest are very different. Okay. So the problem for me when I was a student, this was in 2010, is whatever studies that needed to be done had to have the code fit on one screen. You could not scroll, you could not switch between files. You had to do a ton of post-processing, literally draw circles and rectangles and shapes to create your areas of interest and then map them and do an export. And trust me, it is not very fun to export these large, sparse matrices from Adobe Studio. It is very ugly, actually. At that point, I was like, there has to be a better way to do this. And the next thing is, if we do these studies on small source code snippets, we cannot generalize it. In fact, I will talk a little bit about this ICSE 2019 paper that shows exactly that. But for now, let's get back to think about how the eye trackers work, right? Because this was my pain, is I cannot keep drawing rectangles. Okay, there has to be a better way to do this. So what we did was we basically tried to figure out a way to implement this and incorporate it within the integrated development environment. There was no existing support, no vendor support either, to keep track of what line and which file was present on the screen once you scroll. So my question, I'll come back to the other two, high-speed trackers and editing in a minute, but the question, what I was trying to address is, I looked at even software that you pay for. None of them use this. So there was at the time Toby Studio, there was Ogama as an open source system. The same thing, it uses the images. So in 2010, I was a grad student. I graduated with my PhD in 2010. I asked myself this question: can we enhance development environments to implicitly capture developers' eye movements on artifacts while they work? And yes, we did, obviously. This was possible to do, but it took a while. It took a few years. It took some rejections. I'll show you the timeline a bit later. But we had to provide proof that what we got from eye tracking was much more than just key interactions and mouse clicks. So we did this study. This was published in FSE 2015. I went with my student to, I was in Ohio at the time. I went with my student to NC State, to ABB, and we spent a week there. We collected data from professional developers and students. and basically wrote this paper showing proof that if we ran a study with interaction logging and eye tracking at the same time, we used myelin for interaction to collect interaction data, we get a lot more context with eye tracking. And I think this paper is really what made it believable. We later published the actual framework for eye tracking. We call it eye trace. And that's a cool logo that was created by one of my students. We won Best Paper Award at the Eye Tracking Research and Applications Conference in 2018. And then we also published a bunch of extension of it, because iTrace is constantly being worked on by a bunch of developers, both on my end and on my collaborators' end. And so what is iTrace? Let me explain to you. It is community infrastructure that supports conducting large-scale studies on realistic tasks within integrated development environments like Visual Studio, Eclipse, Atom, and we also support Chrome now. It allows you to record, you can play back, and then we have a basic post-processing event detection system. You can go to i-trace.org to download the version that we currently have, but we will have a new updated version coming up in March. So this is basically what it looks like after a calibration. You might not be able to see that, but that little black window shows you the 9 calibration points with the little dots around it. I can play this for you real quick so you can see. This is just a visualization. At the bottom here is the iTrace controller. And you can see the little reticle that shows you the gaze. And what we did here is we just highlighted the token that you're actually looking at. Obviously, during the study, this is not highlighted. I just have this for demo purposes. So like I said before, our target, and our website talks a little bit more about this, is to support 3 main stakeholders, but you might have more, of course. As a researcher, I want to understand how programmers work. I want to eventually develop theories, collect enough data in the community. We can get there. As educators, we can find out where students are struggling and perhaps help get them quicker to be an expert. And then the stakeholder we forget sometimes is the developer themselves. We would like them as a developer to become more aware of how they work. Sometimes when I play back these things to people, they basically ask things like, why, for example, they'll be like, why was I looking at this? If I replay it to them, they'll be like, I wasn't sure I was looking at this. Why was I looking at it? So some people don't realize. So as humans, we don't really realize what we're looking at in the process, okay? And so this is really useful for these 3 stakeholders. We released an alpha version in 2019, but there's an upcoming release, like I said before. This study was something that we replicated to kind of show that, sometimes when you replicate things, you don't get the same results if you look at just small screens, small snippets. So just quickly, one of the so we replicated, Paige is a good friend of mine. She's at Clemson. She did a study on code summarization at ICSE 2014 with single screen text, obviously, because at the time, that's what people did, including myself. But we replicated the study using iTrace, where you could scroll, you could context switch, you could see the whole system, not just the method you were summarizing. And what we found is a different ranking. We found a different gaze distribution. If you gave a developer the entire system, they actually go and look at things outside of the method they're summarizing. So in our paper that you see on the right, the ranking was they looked at call terms more than the method signature. Whereas if you have a method in isolation, they might have no choice but to look at the method signature. Okay, so the point here is that if you, in an open source system where you have more things to look at, you're going to want to look at other things. And this is just one finding. There are other interesting findings too, but I'll keep it brief here. So they spend longest time reading call terms. Expert tended to revisit the body of the method more frequently than the signature as the method increased. So we had different sizes of methods as well. Okay. We also were able to detect if we could predict if a line was used in the summary based on keywords, based on the gaze time. So this is really interesting for automatic summarization tools in the future, right? So bottom line, replications are important. Size and context matter. Showing methods in isolation will not give you the same results as showing methods within their ecosystem that they are in usually. Okay, so we are coming with the new version in, like I said, March 22 next month. And basically what we have done is we have completely designed it to include support for high-speed trackers. So we were hitting a roadblock basically at a point where the tracker would map the wrong thing that's on the screen if you exceeded 60 hertz. Every tracker comes with a frame rate. I mean, the rate it gives you samples per second. I have trackers ranging from all the way to 1200 hertz, which will not work because basically that's what I'm going to explain next, okay, really quickly. We published this, we actually got a Best Paper Award for this, and we are currently, this paper is under review at a journal submission. So let me explain what this is and what the problem was. Our goal was to run eye tracking studies in real world setups, right? So basically, as a study participant, you come in, your gazes, this is a client server architecture. So you have a core that gets your gazes. The gaze is then sent to the plugins, and the plugins could be Visual Studio, Eclipse, Atom, Chrome. The plugin's responsibility is to map that using its internal AST or API. So it's using a function call to figure out where that particular line or that XY coordinate maps to. Okay, and what this thing actually, there was an issue with the response time. So let's say if we had so this is just a visualization here. If we had a 60 hertz tracker, we would need to complete this lookup in 17 milliseconds. However, Visual Studio, as the number of tabs open increased, this time increased exponentially, as you can see here. Eclipse was much better actually at this than Visual Studio. By the way, we have had a lot of issues with implementing a plugin for Visual Studio. And don't ask about Visual Studio Code because that was not even open source as they claim. So the function that we needed to find the line column is actually closed. We could not use it. Anyway, so obviously we hit a roadblock. So we were not able to, and we were stuck with whatever, we cannot change Eclipse or Visual Studio, obviously. So we were stuck with this response time. And so what we had to do is come up with another solution here. As you can see, with 60 hertz, it's 17, but we have trackers that, and you can see the lookup time goes all the way up to 40. We have trackers that go all the way up to 1200 hertz, which so the lookup needs to be complete in 0.83 milliseconds, and that just would not work. So what would happen is, and we found this bug after we were testing, what would happen is it would not give you an error, but what it would do is it would basically just map the wrong thing. So there was a queue that's filling up faster than it's getting out of. And so the screen is always moving, right? The screen is not waiting for these queued up gazes. And so we would map to the wrong thing. So in our testing, we found this out. So the way we circumvent this is we do all the lookups in a post-processing step, which we call deja vu. So we save during the study. Let's say you had a gaze, a mouse click, a scroll. We store these HCI events during the replay. We play it back, but now because we have saved everything, we can play it back at a much slower rate. So we can get the 1 millisecond to a second and just play it back after the participant is done. We can play it back, and if it finishes in an hour, nobody cares because we can just let it run after. It usually doesn't take an hour, but I'm just saying if it did, it could be slowed down. It could be slowed down until you need it to finish. So that's basically what we did with Deja Vu. So we basically took out the plugins part. We store all the events in Deja Vu. In the recording phase and in the replaying phase, we actually play it back. We tested this and we found that without Deja Vu, we actually lost 41% of the data, and which is definitely not good. So, but with Deja Vu, you hardly lose anything. And this replication package is provided at that link. So the iTrace timeline. So it started off as an idea I had in 2010. The idea was actually realized with proof in 2015 that it actually worked. That was the FSC paper I talked about. We only had the Eclipse plugin at the time. We applied for a grant in 2016, it was rejected, but then we resubmitted in 2017. Finally, it was accepted. We had the first release in 2019. We replicated a study on iTrace in 2019, the ABID study I talked about, the Page Rodriguez study, where we looked at calls more. We also introduced support for high-speed trackers. So the point here is it took many years to get from point A, from the idea to actual release of an actual system. And releasing software, as I've learned, the hard way is not easy at all. Right now, we are writing documentation and testing for our second release, and it's just taking up a lot of time. So hopefully, but it's very well worth it, and I really appreciate the community for supporting us. So what is the future vision? First, we need to ask ourselves what eye gaze can tell us. Okay, and I'm going to just leave a few things here because I want to also answer some questions or listen to what you have, ideas you have. You get a basic set of metrics from gaze, right? You get the number of fixations, duration, your pupil size. Be very careful of using pupil size. I don't use this in, actually none of my papers use pupil size, because if you cannot use pupil size in hindsight. You have to design your study in a way such that you can actually use pupil size as a measure. Number one important thing to do when to use pupil size is to have a chin rest and to make sure your light, even on the monitor, doesn't flicker. So you cannot go from light mode to dark mode or just suddenly change the lighting, because your pupils are going to constrict, and everyone has a certain baseline. So it's a very sensitive measure. This is why I don't use it in hindsight. You have to know that you're going to use pupil size before you do it. And there are other things like blink rate, scan path, and so on. But one thing we could do is replicate studies. We did that with the Rodriguez study, but there's also this Fritz study that is quite interesting. This is also by Fritz, the Inflow and Happy paper. That's one thing you could do in the future, is replicate these studies to see if these things still hold in a larger context. Right now, mostly the eye trackers are used for assessment. So they're trying to do a user study to assess. But why don't we think more than that? Why can't we use an eye tracker to improve the task itself? For example, using eye tracking to help code summarization or code recommendations. In a similar way, like when you use Google search, right? It recommends you something based on the history of how you searched. So if I search differently than you, it's not going to give me the same recommendations as you. The same with gaze. So if we tracked as developers our gaze as we fix bugs in a certain project, it should then be able to learn how our gaze is on these different systems and be able to recommend us starting points or recommendations. I do this a little bit with traceability. You can look at these two papers in 14 and 16 that try to generate links automatically from gaze, but I'm not going to discuss them here. Oh, I want to talk about this sticky point also, because with COVID hitting, a lot of people have started using webcams. Yeah, there is a company called Real Eye. I don't know if you know this, but they offer a webcam solution to eye tracking. And instead of going and buying a high-speed research-based tracker. Do they work? Well, we tested this in the lab. So last year, I ran a course on software engineering for eye tracking in software engineering, and it's a research-based course. And basically, they did a study in there. They used iTrace at the same time as a webcam. And we found that there is very little overlap. In fact, there's only probably, we did it just with 5, it was a pilot study. We haven't published this yet, but we eventually will collect more data to publish this work. It is not nearly as close to the trackers that we have that are actually built for reading. Where does the future lie? So you look at Facebook, Apple, where they're investing things, what patents they have. A lot of this has to do with the VR and AR. And nowadays, a lot of these sets, the HoloLens comes with eye tracking, the HoloLens 2. There's a lot of high-end VR headsets also that have eye tracking. But the question is, what is the consumer application that they can convince us to use? Have you heard of MoviePass? MoviePass is a service that allows users to watch movies for cheap. This summer, they're going to bring it back, and you can only buy movies if you actually watch all the ads. Okay. You cannot just like watch the ad and keep it somewhere and then go and do something and come back. And so I don't know, that's also a privacy concern, right? What else is your eye tracking used for? So this thing, something to think about as software developers, and especially working from home. How could VR and eye tracking be used to leverage better productivity? This is just an open question. Future enhancements for iTrace, we are looking at live correction algorithms after the release. We're looking at supporting editing across the infrastructure. Right now, we only support it in Atom. Visualization of eye tracking data. This is a whole field that people haven't really looked too much into. There are a few people working on it, but I think there's a lot more that can be done. Privacy issues definitely are a concern. Do you want your boss to see what you're looking at when you're browsing Stack Overflow, or are you going off task? What sites are you looking at? And then finally, live streaming. We can do a live streaming also. That's something that is a possibility. But we wrote this paper. It's a practical guide to eye tracking studies in software engineering. It was a joint effort between Zore, Andy, Roman, Martha, myself, and Jan. And basically, it just gives you, whoever wants to get into the field, if you're looking into getting into eye tracking, please read this paper. Ask me questions. I'm happy to answer questions. We collected a really large data set. This was a multinational effort. In 2020, last year, it was published a couple of years back, of 216 participants. Again, this is just on short code snippets, not large snippets. There are not many studies on iTrace. Besides me, myself, I think Venera's student, Sarah, used iTrace, and then another team, 2 or 3 teams are using iTrace so far. But we want that to change. We want more people to use it. We are happy to show you how to use it to support you, to get you up to speed. This is what I live for. I live and breathe eye tracking. I absolutely love if more people want to use it. I want to leave you with this last image, because the task you do in your study, even if it's a software engineering study, is super important. This is an image from Yarbus in 1967, and I show this in most of my talks, is because what prompt you give somebody can change the way they look at things. How people fix bugs is very different than how people summarize a method, right? Or how people just free look at code to see what exists. So as you can see there in the third picture, if the prompt was give the ages of people, you could see the fixations were directly at the faces. Okay. I want to leave time for questions. So this is my team. I really want to thank them. All of them have worked really hard. Please go to our website and download the software. Even if you don't have a tracker, you can use the mouse as a proxy to test it out. And with that, I end my talk, and I'm happy to take any questions.